So in this lecture, I will prove Kolmogorov 3 series theorem. So throughout this lecture, xj will consist of a sequence of independent random variables. And what we would like to investigate is the convergence of the partial sums. So let me represent by Sn the sum of xj from 1 to n. And we are looking for sufficient conditions for Sn to converge almost surely. So I'll start with a theorem which is the so-called one series theorem, and which reads as follows. So again, I will always assume that xj are independent from variable. So now let's assume that these random variables have finite second moments and that they have mean 0. So I'm assuming that the expectation of xj is equal to 0 for all j. And I'm assuming that the variance of xj, which I'm representing by sigma squared j, which in this case is the expectation of xj, it's finite. So now what I claim is the following. Well, assume that the sum of the variance it's finite, and then I claim that Sn converge almost surely. And the proof, well, I give two proofs. The first one, first point is that to show that Sn converge almost surely, it's enough to prove that it converges in probability. We have seen that in the previous lecture. So we have to show that actually Sn converge in probability. And to prove that it converges in probability, it's enough to guarantee that Sn it's a Cauchy sequence in probability. So remember, to prove that it's a Cauchy sequence in probability, we have to show that for all epsilon positive, the probability that Sn minus Sm it's larger than epsilon, that this converge to 0 as n and m converge to plus infinity. But now, well, if I want to bound that, I can use Chebyshev inequality to say that this, let me take the square and then use Chebyshev inequality to bound that by 1 over epsilon square, the expectation of Sn minus Sm square. Now, by definition, this is 1 over epsilon square, the expectation of the sum for j going from m plus 1 up to n of xj square. And since now I expand this square, I compute the expectation. Since the random variables are independent, the expectation of the cross terms are equal to the product of the expectations, but the expectation are equal to 0. So that this is equal to 1 over epsilon square, the sum from j from m plus 1 to n of sigma j square. And since this sum is finite, this expression it's converging to 0 as m and n are converging to plus infinity, and therefore this proves that indeed this probability converges to 0 as n and m converge to plus infinity, which means that Sn it's a Cauchy sequence in probability, and therefore it converges in probability, and therefore it converges almost surely. So this is one proof. I'll give you a second proof in which we get so now I claim that actually the probability that the maximum from m to n of sk minus sm, that this converges to 0 for all epsilon positive as n and m converge to plus infinity. So now I'm giving you a second proof of the same result. And instead, by estimating that, proving that S forms a Cauchy sequence in probability, I will estimate this quantity. And what I claim is that for all epsilon, as m and n go to infinity, this probability vanish. Well, and this will follow by Kolmogorov maximum inequality. So let me rewrite this difference. So this is a maximum from k between m and n of the sum for j going from m plus 1 up to k of xj. So this is just by definition of S. Now I will, to apply Kolmogorov inequality, I want to rewrite this as the probability that this maximum. So now I want, instead of k going from m to n, just to have exactly the statement of Kolmogorov maximum inequality, I'll do that as k going from 0 to m minus n. So what I'm doing is that I'm replacing k by k minus m. And doing so here, I have a sum. And this sum, it's going from m plus k to m plus 1 of xj. Well, the same thing here. I'm just subtracting m. So I'm taking k minus m from 0 to n minus m. And now I'm replacing k minus m by k prime and k prime. So this k will become k prime plus m. So you can check that these two quantities are equal. And now instead of writing this, I will just rewrite that as a sum. So this is a sum from j equal to 1 up to k of x m plus j. And these are, let me call these variables yj. So now yj are independent random variable. They have mean 0. And therefore, by the Kolmogorov maximum principle, what I have here is that the maximum for k less than m minus m of the sum from 1 up to k yj larger than epsilon. And we have seen that this is bounded by 1 over by, so this is Kolmogorov maximum inequality. So this is bounded by 1 over epsilon square. And then the variance of the last term, which is, or the expectation of the last term, which is the sum from 1 up to m minus n of yj square. And this is equal to 1 over epsilon square, the sum. So this is, again, the sum from and this is n minus m, of course. I'm sorry, here, this is n minus m. Everywhere here, it's n minus m because, well, n is the larger one. And here, so I have the expectation of yj square, but yj, it's xm plus j. So this is xm plus j square. And now by changing the variables, this becomes 1 over epsilon square, the sum. Now, this sum starts from m plus 1, and it ends in n of the expectation of xj square. And this you see as since this sum is finite, as m and n go to infinity, this sum goes to 0. So we proved indeed that this probability is going to 0. Since this probability is going to 0, we have seen that in the previous lecture. So that proves this claim, and it follows from these claims that S and converge almost surely to a limit. So this is exactly what we were claiming, and therefore this completes the second proof of this first theorem, in which, I repeat, we have a sequence of independent random variable. They have mean 0, they have finite second moment, and this theorem states that if the sum of the second moments is finite, this implies that the sequence of partial sums converge almost surely. Now I have a second theorem, which is a two-series theorem. Xj is still a sequence of independent random variable, but I'm not assuming anymore that they have mean 0. I'm calling Xj, the expectation of Xj, as Aj. And I don't know if I have defined already, but if I have a random variable x such that the expectation of x squared is finite, I will call the variance of x the expectation of x minus its expectation squared. And this is equal to the expectation of x squared minus the expectation of x squared. And so I'm assuming here that the variables are independent. They have finite mean, and actually they have a finite second moment. And I noting by sigma j square the variance of xj. And the theorem states that, well, if the partial sums of Aj converge, and if the sum of the variance is finite, then Sn converges almost surely. And this, well, theorem, it's a simple consequence of the previous one. Let me define, so here is the proof. Let me define Yj to be Xj minus its expectation. So Yj, it's a sequence of independent random variables. They have mean 0, so the expectation of Yj is equal to 0. And the expectation of Yj squared, it's equal, by definition of Yj, it's the expectation of Xj minus the expectation of Xj and this square, which is what we called sigma j square. So this is the variance of sigma j, and this is sigma j square. By assumption, sigma j square, the sum of sigma j square, it's finite. So this means that the sum of the expectation of Yj square, it's finite, and therefore the three assumptions of theorem 1 are satisfied, and therefore this implies that the partial sums of Yj converge almost surely. So the partial sums of Yj converge almost surely, but what is Yj? By definition, this is Xj minus its expectation, the expectation of xj, we denoted that by aj. So we know that this sequence converge almost surely. But we also know by assumption that the sums of aj converge. Since the sum of aj converge, and since this difference converge almost surely, it follows from that that the sums Sn converge almost surely. So this second theorem, it's a very simple consequences of the first theorem. Well, we finally reached the tree series. But before I state the theorem, I want to give you the idea. So we have xj, the sequence of independent random variable, and we wish to find sufficient conditions for the sum to converge almost surely. Well, we know already that if we have a sequence in which the expectation of xj converge and the variance of xj is finite, then we know that the partial sums converge. This is the two-series theorem. Now, let me consider this sequence of independent random variables, and let me fix a constant c, which is strictly positive. And let me define yj as the sequence xj truncated at the level c. So xj, it's equal to xj if the random variable xj, it's bounded by c. So in other words, yj, it's equal to xj if xj, it's bounded by c, and it's 0 otherwise. So these random variables yj are independent because the xj are independent. And, well, assume that the probability that xj is different from yj infinitely often, it's equal, the probability of this event, it's equal to 0. So this means that, well, xj different from yj infinitely often has probability 0. So this means that if I call this set A complement, I have a set A which has probability 1, right? And if I take omega in A, this means that it doesn't belong to this. So this means that there exists n0, which depends on omega, such that xj of omega is equal to yj of omega for all j larger than n0 of omega. Right? So if omega belongs to A, which is the complement of this set, what is the complement of xj not equal to yj infinitely often? It means that, well, starting from some index, they are equal. So this means that there exists an index n0 such that starting from that index, xj and yj are equal. Well, but if this is true, this means that the sum of xj converge of xj omega converge if and only if the sum of yj of omega converge. Right? They may differ in the first n0 terms, but starting from n0, they are all equal. So this sum will converge if and only if this sum converge. So if we can prove that this set has probability 0, so if we can prove this condition, and if we have conditions which guarantee that yj converge, then this will force xj to converge. And what are the conditions? Well, we have seen now we have yj, it's a sequence of independent random variables. They have finite second moments because they are bounded by C. So we know that this sum converge if two conditions are matched. The first one is that the expectations of yj converge. So the first condition is that the sum from j from 1 to n of the expectation of yj converge. And the second one is that the variance of yj converge. So what I claim is that if this sequence in n converge, if the sum of the variance of yj is finite, and if this set has probability 0, so if this condition is matched, then the Sn, the sequence, the partial sequence, the partial sums of xj converge almost surely. And why is that so? Well, because yj, according to these two conditions, the partial sums of yj converge almost surely, and by this condition, well, they are equal. If yj converge, then the sum of xj converge. So we reach a theorem which tells us that, well, if for a certain C, I define this sequence of random variable, if this sequence of random variables satisfies these two conditions, and if, moreover, we can prove that this condition holds, then the sum of xj converge almost surely. So this is the three-series theorem. I hope I convince you that it works. And now I will state it properly and I will prove it, just to make sure that you understood everything. And well, so this is the next step. So here is the theorem. xj is still a sequence of independent random variable. And I'm fixing C. Suppose that there exists real number C, strictly positive, such that the following hold. I define the sequence yj to be equal to xj if xj is bounded by C, and 0 otherwise. So this is a new sequence of independent random variables. I assume three conditions. This is why it's called the three-series theorem. I assume that the probability that xj different from yj, that this is summable. That condition by Borel-Cantelli will imply that the probability that xj is different from yj infinitely often is 0. Then the second condition is that the partial sums of the expectations of yj converge. So this is a sequence of real numbers, and I'm assuming that this sequence converge. And then finally, I assume that the sum of the variances of yj, it's finite. Then, under these three conditions, I claim that Sn, which is these partial sums, converge almost surely. So this is the statement of the three-series Kolmogorov theorem, and the proof, which I already presented, is as follows. So I will repeat it. Well, it follows. First, it follows from Borel-Cantelli lemma that, well, since we have this infinite sum finite, we know that the probability that xj is different from yj infinitely often, that this is equal to 0. So this follows from Borel-Cantelli lemma. So this means that the sum of xj converge almost surely if and only if the sum of yj converge almost surely. Right? Because in the complement of this set, which has measure 1, yj and xj are equal from one point on, and therefore, well, if this sum converge, that sum converge, and conversely, if this sum converge, that one converge. So in order to prove that these partial sums converge almost surely, it's enough to prove that the partial sums of yj converge almost surely. Well, but by the two-series theorem, it follows from these two conditions that the partial sums of yj converge almost surely. And therefore, the partial sums of xj converge almost surely. So this completes the proof of these three-series theorem. What is remarkable is that, and this is my next step, is that actually these three conditions are not only sufficient to guarantee the convergence of this sequence, but they are also necessary. So this will be the second part of this lecture, in which we'll show that, well, if this sequence, if we have a sequence of independent random variable, and if the partial sums converge almost surely, then for all A, for all C, these three conditions are satisfied if I define yj in this way. Therefore, that proves that if this condition is satisfied for one C, it is satisfied for all C. Because if it's satisfied for one C, then by this result, the partial sums converge almost surely, and I'm claiming that if the partial sum converge almost surely, then these conditions are satisfied for any C. Therefore, and this is quite surprising, quite remarkable, if this condition is satisfied for one C, it is satisfied for all real number C. So before I prove the converse, I want to give you an example of an application of this theorem. So here is an application. I consider Zj a sequence of IID random variables. And the probability that Zj is equal to 1, it's equal to 1/2, and this is also the probability that Zj is equal to -1. So these random variables take the value 1 and +1, each one with probability 1/2. And what I'm interested in is to consider the partial sums from 1 to n of Zj divided by j. So you see, sometimes we know that this series is not converging. If you take the absolute value of these terms, well, it is a divergent series. But now, and you know also if you take these alternate, so if you take 1 over n minus 2 over n, 1 over 1 minus 1 over 2 plus 1 over 2, 1 over 3 minus 1 over 4 plus 1 over 5 and so on, so that this sequence is convergent, but if you take the absolute values of each term and you sum them up, it's diverge. And now what you do, well, you take, well, these signs will be plus or minus with independently and with probability 1/2. And you want to investigate, well, if this sequence converge or does not converge. Right, so it's a reasonable question, and we will just apply Kolmogorov three-series theorem. So if I define xj to be Zj divided by j. This is a sequence of independent random variables. Of course, they are not identically distributed anymore. But what do we know? Well, we know that xj, it's bounded by 1 over j, so it's bounded by 1 for all j. So let me take in the previous theorem, c equal to 1. Now, if I take c equal to 1, what I get is that yj, it's equal to xj for all j. Because, well, xj, it's bounded by 1, so yj, it's equal to xj for all j. If I cut off xj at level 1. So the first condition of the three-series theorem, it's of course satisfied because they are just equal for all j. So this is the first condition. Then the second condition, it's, well, we will look at the sum of yj from 1 to n. But this is the sum from 1 to n of 0 because the expectation of yj, which is the expectation of xj, it's equal to 0. So the second condition is, of course, satisfied because, well, the expectation of yj is 0. So this is the second condition of the theorem. And finally, the third condition of the theorem was about variance. But here, the variance of yj, it's the variance of xj. And the variance of xj, you see that if I take the square of zj, this is 1. So the variance of xj is 1 over j squared. And the sum of 1 over j squared, it's finite. So the three conditions of Kolmogorov three-series theorem are satisfied, and therefore this sequence, the sum, the partial sums of xj, which means the partial sum of zj divided by j, converge almost surely. And of course we can, well, we don't need to divide by j. You see that the same argument will work if you take j to the power theta, provided that theta it's larger than 1/2. So if I take any theta larger than 1/2, I define xj in this way. I still have that the three conditions of Kolmogorov three-series theorem are satisfied, and therefore that this sequence it's well, converge almost surely. Well, now of course, if I take theta between 0 and 1/2, including 1/2, the last condition is not satisfied, and therefore, by the converse of the three-series theorem, the sequence does not converge anymore. So I didn't prove it yet, I will prove it now, but once we proved that if this sequence converge, then these three series converge for all value c, then it will follow from this result that if I take theta between 0 and 1/2, including 1/2, this series does not converge anymore. So if theta is less or equal than 1/2, this series cannot converge almost surely. So I will state now the converse of the three-series theorem, and then I will prove it. So here is the converse theorem. I have xj, a sequence of independent random variables. I call Sn the partial sums, and I'm assuming that Sn converge almost surely. Then what I want to prove is that fix some c or some a positive, define yj as the random variable xj truncated at a. So this is xj if xj it's bounded by a and 0 otherwise. Then I claim that the probability that xj is different from yj, it's finite. I claim that the sum from 1 to n of the expectation of yj converge. And I claim that the sum of the variance of yj, it's finite. So again, I'm assuming that Sn converge almost surely. I'm fixing, you fix any a. So this is true for all a. Define yj as the variables xj truncated. And then I claim that this series is fine. It's finite. That the partial sums of the expectation of yj converge. Remark that, well, yj, the expectation, it's well defined because yj is bounded by a. So this is well defined. And what I claim is that this sum, this sequence converge, and then that these variants are finite. So before I prove that, I will prove a weaker statement which will be used in the proof of this theorem. So as I said, I will state a weaker theorem. I'll state a lemma. I left the statement of the theorem just to compare. And instead of using x, I will use it y. So I have a sequence yj of independent random variables. And I am assuming that the expectation, so here is the extra assumption, that the expectation of yj are equal to 0, that the yj are bounded by some constant c. Okay? So I'm assuming that I have a sequence of independent random variables. These random variables, I'm assuming, are bounded by c, and they have mean 0. So these two conditions were not in the theorem, so they are extra conditions. So this is why I'm saying that this lemma is weaker than the previous one. And then we have the same hypothesis. I'm assuming that the partial sums of yj converge almost surely. And then what I claim is that the variance is finite. So the sum of the variance is finite. So if you compare the difference here, it's that I'm assuming now that the variables xj, which now I'm calling yj, are bounded. This is for all j, so that there exists a constant so that yj is less or equal than c with probability 1. Therefore, the expectation of yj is well defined. I'm assuming that it has mean 0. And I'm also assuming that the sequence, the series, the partial sums converge almost surely. And then what I'm claiming is that it follows that the variance is finite. And okay, so this is the lemma. I will now erase the statement of the theorem. I will prove the lemma, and then I'll go back to the proof of the theorem. So I wrote here the assumptions of the lemma. Yj are independent random variables. They are bounded. They have mean 0. I'm assuming that the partial sum is converging almost surely. And what I claim is that the variance, it's summable. And here is the proof. So the proof, it's divided essentially in two parts. So let's go to step 1. And in step 1, I'll fix a real number L, and I will define ANL as the set of omegas such that S1 it's bounded by L, S2 is bounded by L, up to Sn bounded by L. So A and L is the set of omegas such that S1 of omega is bounded by L, S2 of omega bounded by L, Sn of omega bounded by L, and here S1, S2, Sn are the partial sums, but instead of x, I have y, right? So this is what I'm now calling Sn. And my claim is that there exists L finite and delta positive such that the probability of A and L it's larger than delta for all n. So I can find, what I'm claiming is that I can find strictly positive delta and a finite L for which the probability of this set is larger than delta for all n larger than 1. And let me prove this claim by using the fact that this sequence is converging almost surely. So what I know is that Sn it's converging to S almost surely. Well, what does it mean? It means that for all epsilon positive, there exists n0 such that Sn minus S it's bounded by epsilon for all n larger than n0. So let me write this event in terms of sets. For all epsilon, it means that for all k larger than 1, I'm taking epsilon as 1 over k. There exists one n larger than 1, such that for all p larger than n, I have that Sp minus S, it's less than epsilon. So this is the set in which Sn is converging to S, and therefore, since this conversion happens with probability 1, this means that this set has probability 1. And here I'm taking 1 over k. Epsilon, it's 1 over k. So I know that for all k, this probability is equal to 1. Therefore, this implies that for all k, this set, the probability that the union for all n, the intersection for all p larger than n, that Sn minus S less or equal than 1 over k, it's equal to 1. Right? If this set has probability 1, this means that this is an intersection. This means that all k, this set has probability 1. And I'm not using very much here. I'll just take k equal to 1. So I know that this set here has probability 1. And now you see, as this is a set which depends on n, right? So this, let me call that Bn, if you wish. And since as n is increasing, I'm taking intersection of less and less set. This means that this sequence is increasing, and it's increasing to its union. And therefore, the probability of Bn is converging to the union, but the union has probability 1. So this means that the limit, as n goes to infinity, of the probability that the intersection for p larger than n, that Sn minus S less or equal than 1, that this limit is equal to 1. Right? Because, well, the sequence of sets is converging to the union, and therefore the limit of the probability of these sets is converging to this probability of this union, and this is 1. Well, but since this probability is 1, this means that, well, for n sufficiently large, this probability is larger than 1 minus delta. So there exists n0. So I'm fixing a delta strictly positive, and what I get is that there exists n0, finite, such that the probability of this set is larger or equal than 1 minus delta. So the probability that Sn minus S is less or equal than 1, the probability of this set it's larger than 1 minus delta. And here delta is small, say delta it's a small number, and for this and 0 depends only on that delta. So that's fine. So now, since S, so I know that Sn is close to S for all Sp, Sp, it's close to S for all p larger than n0. Now what I claim is that S is small. Since S is a random variable, the probability that S is larger than A, the limit as A tends to infinity, so that this is equal to 0, as it's a random variable, so it takes real values, and therefore this probability is converging to the probability of the event that the absolute value of S is equal to plus infinity, and this is 0. Therefore, we know that this limit holds, and again, so I know that there exists, given that delta, I know that there exists an A such that the probability that S is larger than A, that this is smaller than delta, and therefore that the probability that S is less than A, this is larger than 1 minus delta. So I have a set here which has probability larger than 1 minus delta, and a set here which has probability larger than 1 minus delta. What I claim is that the intersection has a probability larger than 1 minus 2 delta. So this is clear, but let me show it to you. So what I'm saying is that suppose that you have two sets, A whose probability is larger than 1 minus delta, and B whose probability is larger than 1 minus delta. What I claim is that this implies that the probability of the intersection of AB is larger than 1 minus 2 delta. And why is that? Because if I take the complement of this probability, so the complement of AB, so this is equal to the probability of A complement union B complement, and this is bounded by the probability of A complement plus the probability of B complement. And we know that the probability of A complement is bounded by delta. The probability of B complement is bounded by delta. So the probability of the complement of intersection B is bounded by 2 delta, and therefore the probability of intersection B is larger than 1 minus 2 delta. So I want to apply this inequality to those two sets. So what I have is that the probability that S is bounded by A, and that the intersection for P larger than n0 of Sp minus S bounded by 1, this is larger than 1 minus 2 delta. Okay, so this bound follows from this bound, and this simple observation. Fine, but once we have this bound, well, if S is bounded by A, and if Sp minus S is bounded by 1, this means that Sp is bounded by 1 plus A. So this set, it's contained in the set such that for all P larger than n0, Sp, it's bounded by 1 plus A. Right? So if S is bounded by A and Sp minus S is bounded by 1, by the triangular inequality, Sp it's bounded by 1 plus A. And therefore, since this set is contained in that one, the probability of this set is less or equal than the probability of that set. But since the probability of this set is larger than 1 minus 2 delta, the probability of this set it's also larger than 1 minus 2 delta. So, well, we are almost there, because what we are proving is actually stronger than that. We are saying that for all p larger than n0, Sp it's bounded by 1 plus a, with a probability bounded below by 1 minus delta. So we are making this probability almost 1, and here instead of having a finite number, we have an infinite number. But we are still missing the first ones, p equal to 1 up from 1 up to n0. But that, let me take a j. I will use the same argument, the probability that Sj it's larger than b, that this goes to 0 as b goes to plus infinity. Sj it's a random variable, so it's the probability that Sj it's larger than b. Well, this goes to 0 as b goes to plus infinity, and therefore I can find a b such that this probability it's bounded by delta divided by n0. Okay, n0 is this one. Delta, it's this small quantity which I fixed at the beginning of this proof, and therefore I can find a b large enough for this probability to be bounded by delta n0. So this b depends, of course, on j. I do that for j between 1 and n0. I take b as the maximum of bj. And now what I get is that, well, the probability that the maximum of Sj larger than b, so the probability that this maximum, j running from 1 to n0 of Sj larger than b, beats this maximum, I claim that, well, this probability, it's less or equal. So if this maximum is larger than b, this means that there exists one which is larger than b. So this is bounded by the sum from j from 1 up to n0 that Sj it's larger than b. But if Sj it's larger than b, since b is the maximum, this means that Sj it's also larger than bj, and bj has been chosen so that this probability is bounded by delta divided by n0. Here I have n0 term, so this is bounded by delta. So this probability it's bounded by delta. Since this probability is bounded by 1, it's greater or equal than 1 minus delta, what I get by the same argument as before is that the probability that the maximum between 1 Sj larger than b, smaller or equal than b. So let me take the complement of this set. So the probability of the complement is larger than 1 minus delta. The probability of this set has probability larger than 1 minus 2 delta. So what I get is that this set has probability bounded by 1 minus 3 delta. Yeah, and then we are done, because if I take C to be the maximum between B and 1 plus A, what I get is that the probability that the maximum for all g larger than 1 of Sg smaller or equal than C, this is larger than 1 minus 3 delta. Okay? If I take C because, well, if this maximum it's bounded by C, B, it's bounded by C. If this intersection it's bounded by 1 plus A, it's also bounded by. And since here I'm taking care of the first n0 terms, and here I'm taking care of the remaining terms, I have that actually all terms are bounded by C, where C is this maximum with a probability at least 1 minus 3 delta. So if I take a delta smaller than 1/3, I get the existence of a strictly positive for which this is true. We prove slightly better estimate. We prove that actually this is true for all n. So all the S are bounded by this C. So this is the first step. So we just proved that indeed there exists a finite L and a strictly positive delta for which this set has probability at least delta for all n. Now starting from this bound, we will prove that indeed the variance of Yj is finite. It's summable. So let me just erase L from this. L is fixed. Let me erase it from the notation. And what I want to do is to take a bound on an Sn square dp. Actually, n, yes, minus 1. So I want to estimate the expectation of Sn square on the set an minus 1. I'll get a lower and an upper bound for this quantity. Let me start with the upper bound. For the upper bound, let me rewrite Sn. Okay. So here I have an integral over an minus 1. Let me rewrite Sn as Sn minus 1 plus xn squared plus yn. Now I'm expanding this square. So this is an minus 1 Sn minus 1 square dp. Then I have the cross term. The cross term, it's expectation yn Sn minus 1 on the set an minus 1. You see that the set an minus 1 depends only on the first n minus 1 variables y. And also Sn minus 1 depends only on the first n minus 1 variables y. While yn, it's independent of all this. So the second term, it's equal to the integral over an minus 1 Sn minus 1 dp yn dp. Right? Because what I'm doing here, so let me take a moment to convince you of that. What I'm doing here is that I have Sn minus 1 yn dp. And that I'm writing as chi an minus 1. So when I write this integral, what I'm meaning is that I'm taking the integral and multiplying the function by the indicator of the set an minus 1, Sn minus 1 yn dp. So this first piece, it's a function of y1, yn minus 1. Right? The set an minus 1 depends only on the first n minus 1 variables as well as Sn minus 1. So we know that, so this set, it's independent from yn, and since these variables are independent, and therefore, by a previous theorem, the expectation is equal to the product of expectations, and this is exactly what I wrote here. There is a 2 missing, but that doesn't matter, because now let me use the assumption that the expectation of yj is 0 to say that this integral is equal to 0, and therefore the cross term is equal to 0. And then we have the last term, and the last term it's yn squared. So here you see that I have an minus 1. So this is the probability of an minus 1. And now the expectation of yn square. So again, I'm using the independence between an minus 1 and yn. And the expectation of yn square, it's since the expectation of y is 0, this is the variance of y. Let me represent this variance by sigma j square. So what we get here is sigma n square. And you see, by assumption, the probability of an minus 1, it's bounded by delta. And here, of course, I'm assuming here that n it's larger than 2. Okay, I'll just come back in the case in which n is equal to 1 to see what we write. But let's say that here, since n it's larger than 2, an minus 1 it's larger than 1, and therefore, by this inequality, this is bounded by, so I have the first term, which is an minus 1 Sn minus 1 square dp, and plus this probability it's bounded below by delta, sigma n square. So this is the lower bound. I said that I would prove an upper bound. Actually, I proved the lower bound for this expression, and this is the lower bound we get provided n it's larger than 2. For n equal to 1, let's see what is the bound. So I'll say that A0, it's the whole set, which let me call it omega. And so what we want here, it's a bound for S1 omega dp. And, well, this is equal to x1 square dp. And this is sigma 1 square. Okay. And this sigma 1 square, and I'm always writing x instead of y. I'm sorry, this is y. And well, delta, it's bounded by 1, so it's clearly delta sigma 1 square. So for n larger than 2, we have this bound. And for n equal to 1, we have the same bound, where if I understand that Sn minus 1, S0 is 0. So we can write this inequality for all n larger or equal to 1, provided we understand that S0 is equal to 0. So I wrote here the inequality we just proved, the lower bound. I have that this interval is bounded by this one plus this term, and here the conventions that A0 is omega and the whole set, and then 0 is 0. Now I want to prove an upper bound for that. And for the upper bound, just remark that these sets, as n increase, they are decreasing. Right? So an, it's decreasing. So we have here the set A1, then A2, and so on. And okay, because we are taking an intersection over a larger and larger number of elements. So here we are doing an integral over the set an minus 1, but I want to rewrite that as an integral over an. And then the complement. An, it's contained in an minus 1. So I have here an minus 1 minus an Sn square. But Sn square, I will write it as Sn minus 1 plus yn. And now finally I wrote y instead of x. I want an upper bound, so I have here this one, I will leave it as it is. And for the second term, well, I have this is an integral over an minus 1. So I know that Sn minus 1, since we are on the set an minus 1, Sn minus 1, it's bounded by L. So this term here, it's bounded by L. And Yn, it's bounded by C. So this term here, it's bounded by C. And therefore, this expression, it's bounded by L plus C square times the probability of this set. Right? And so this is the upper bound for this expression. So we have that this expression is bounded by that one, and it's also larger than this expression. So now I will use that this expression, it's bounded by this one, which is bounded by that one, and I'll put this term on the other side. So what I have is that delta sigma n square, it's less or equal than this term, an Sn square dp, minus this term, which is an minus 1 Sn minus 1 square dp, plus L plus C square, the probability of an minus 1 minus an. Note that in the case in which n is equal to 1, so this is omega, I have here S1 square, and what I wrote that the expectation of y1 square, it's bounded by a1 y1 square plus omega minus a1. And this is bounded by, so here I'm using the same convention that a0, it's omega, the same convention I used in the lower bound. So this is the expression we get with the convention that S0 is 0 and A0 it's omega. So this is an inequality which holds with this convention for all n larger equal to 1. So now what I want to do is to sum these inequality. So by summing this inequality for n going from 1 up to p, what I get is that delta n going from 1 up to p of sigma n square. So we get here, this is a telescopic sum. It is bounded by the last term, which is p, ap sp square dp, minus the first term, but the first term is n equal to 1. So, and we adopted the convention that for S0 it's 0. So this is 0. So there is no first term. And then we have this sum plus L plus C square, the probability, the sum n going from 1 up to p of the probability of an minus 1 minus ap, an. And you see that you start with n equal to 1. N equal to 1, this is omega and this is a1. So in my picture, it's the complement of a1, so this is the first term. Then for n equal to 2, this is a1 minus a2. a1 minus a2, it's this annulus. So all these sets are disjoint, and therefore the sum of this probability, it's bounded by the probability of the union, which is bounded by 1. So this sum, it's bounded by 1 for all p. And on the other hand, on the set AP, SP, it's bounded by L. So this expression here, it's bounded by L square, because I have a square. So we get now a bound which is independent of P. For all P, delta times this sum, it's bounded by L square plus L plus C square. So what we concluded is that delta times the sum from 1 up to P of sigma n square, now this is bounded by L square plus L plus C square, and this holds for all P. And therefore, the sum of the variances, it's bounded by this expression divided by delta, and this is exactly the statement of the lemma, that under these three conditions, the series of the variance, it's finite. So that proves the lemma. So I stated here the lemma we just proved. Yj independent, bounded, expectation 0. If the series converge, then the variants are finite. And here, the theorem which we wanted to prove, xj independent, I'm assuming that the partial sums converge almost surely. I'm fixing an A. I define yj as xj cutted at A. I want to prove that these three series converge. So these converge. Then I'll go step by step. I'll first prove this, that the first series converge. So proof. Let's fix A. Let me define yj in this way. I want to show that xj, that this series converge. Well, since Sn converge almost surely, this means that xj, the sums of xj, they converge almost surely. And if this series converge almost surely, so take an omega, this means that there exists an omega, there exists an n0 which depends on omega, such that xj, it's smaller than A for all j larger or equal than n0. Right? For this sequence to converge, well, the terms have to go to 0, and that means that there exists n0 for which xj it's smaller than A for all j larger than n0. And this means, by definition of yj, that xj it's equal to yj for all j larger than n0. And therefore, this means that xj, so w, does not belong to xj equal or different from yj infinitely often. Right? So we proved that if Sn of omega converge almost surely, then omega does not belong to this set, because for xj of omega, it's equal to yj of omega for all j larger than a certain n0. So this means that this set has probability 0. Right? Because if omega belongs to this set, which has probability 1, so this means that a set of probability 1, it's contained in the complement of this set, and therefore this set has probability 0. So the probability that xj different from yj infinitely often, that this is equal to 0. Now let's look at this series. The series that xj different from yj. Well, there are two possibilities. Either this series is finite, or it's equal to plus infinity. It's a dichotomy. Well, since xj you see, yj, it's a function of xj. So the couple xj, yj, it's independent from xj plus 1, yj plus 1. So these pairs are independent, which means that this is a sequence of independent events. And therefore, by the Borel-Cantelli lemma, well, if this is finite, then, so in the first case, the probability that xj different from yj infinitely often, this probability it's equal to 0. While on the second case, the probability that xj different from yj infinitely often, that this event has probability 1. Well, but since we know that this event has probability 0, this must be the case, right? Because if this is the case, we would get 1, and this is a contradiction. So it follows from the fact that xj is different from yj infinitely often has probability 0, that this series has to converge. Because if it diverge, then the probability of this event would be equal to 1 by the Borel-Cantelli lemma, because these events are independent, and this is not the case because we proved that this probability is 0. Therefore, the first part, the first claim, it's proved. Indeed, this series has to be summable. Now, in order to prove the second step, I want to first make an observation. Assume that you have a family Zj of random variables. I'm not assuming them to be independent, just a sequence of random variables, and assume that Zj converge almost surely. Now let me take another sequence, Zj prime, and I'm assuming that Zj prime has the same distribution than the sequence Zj. And what do I mean by the same distribution? This means that for all n, and for all b1, bn in the Borel sigma algebra, the probability that z1 belongs to b1, zn belongs to bn, it's equal to the same to the probability that z1 prime belongs to b1, zn prime belongs to bn. So I have two different sequences. They have the same distribution in this sense, that if I take any n, and capital N, and any b1, bn in the Borel sigma algebra, this probability is exactly the same if I replace z by z prime. And assume furthermore that, so they have the same distribution, and zj converge almost surely. Then what I claim is that zj prime also converge almost surely. And well, this is, I could leave that as an exercise, but let me prove it since I'm going to use it in this proof. Well, I know that zj converge almost surely if and only if it's a Cauchy sequence almost surely. What does it mean that it's a Cauchy? It means that for all epsilon positive, there exists n0 such that if p and q are larger than n0, then as z p minus zq, it's bounded by epsilon. So this means, in terms of probability, that the probability that, let's say that for all, okay, an intersection for k larger than 1 of the union for n larger than 1, the intersection of p and q larger than n, zp minus zq less than 1 over k, that this is 1. So zj converge almost surely means it's the same thing as z forms a Cauchy sequence, and to form a Cauchy sequence, it's that this set has probability 1. So we have seen that, well, since this intersection it's equal to 1, this means that this is equal to 1 for all k. And, well, these sets are increasing, so the probability of the union is equal to the limits of the probability, so that's the same thing as saying that the probability as limit as n goes to infinity of this probability is 1. I'm going fast here because I already used or showed this argument in this lecture. Now here I have P and Q larger than n, knowing that the distribution of the same concerns only a finite number of indices, while here we have an infinite number of indices. So I can reduce that to a finite number by saying that, well, the probability of this event is the same as the union for all P and Q larger than n, but say less or equal than L. So this intersection, I'm sorry, this is the intersection over all now P and Q between n and L, and I'm taking here the union over L. And this is the same set as this one. He's saying that for all P and Q this difference happens is the same thing that for all L larger than n this happens. And since, well, this is an increasing set in L, this is the limit. So I can write that probability as the limit in n, the limit in L of these probabilities. And now I have a finite number of indices, so I can use the fact that z prime and z have the same distribution to replace here z by z prime and go in the other direction to conclude that z prime it's a Cauchy sequence and therefore it converges almost surely. So that proves that if I have two sequences which are equal in distribution, if one of them converges almost surely, then the other one converges almost surely. And I'm going to use this fact in now the second step. Now, step 2 in this proof, I claim that the sum of yj converge almost surely. And that's clear because I know that the sum of xj converge. This is by hypothesis. And also, I know that yj equal to xj. So for all with probability, so okay, let me write that, yj not equal infinitely often, so that this is probability it's equal to 0. So that means that in a set of probability 1, we have so there exists a set A, which has probability 1. And if omega belongs to A, there exists n0 of omega such that xj of omega it's equal to yj of omega for all j larger than n0. Right? And since, well, this series converge, and since yj coincides with xj for all j larger than n0, in the intersection of the sets in which this series converge and A, also y converge, and this set has probability 1. So this means that indeed this sequence yj converge almost surely. So we know that yj converges almost surely. And now what I will do is I will take yj prime, a sequence which has the same distribution as yj. same distribution as the sequence yj. And we have seen that since they have the same distribution, the sums have the same distribution, and therefore the series of yj converge. So this implies that yj prime from 1 to n converge almost surely. And let me define wj as yj minus yj prime. So this is a sequence of independent random variables. So they are independent. Yj, it's bounded by yj plus wj, it's bounded by yj plus yj prime, and yj and yj prime are bounded by a. So yj, it's bounded by 2a. And the expectation of yj, of wj, it's equal to the expectation of yj minus the expectation of yj prime. And since they have the same distribution, this is 0. So note that I'm defining these sequence yj prime. I want them to be independent from yj. So I'm constructing a product space, yj and yj prime. And I'm constructing this sequence in this product space in such a way that, well, they have the same distribution of yj. So this means that these variables are independent. Because, well, yj is independent from yk by definition, and yj is also independent from all yj because yj prime, because we constructed them in a product space. So indeed, wj forms a sequence of independent random variables. Well, so now observe that we are exactly under the assumptions of the lemma. We have a sequence of independent random variables, wj. They are bounded. They have expectation equal to 0. And they converge almost surely because the sum of yj is converged, the sum of yj primes converge, and therefore the sum of yj prime, yj minus yj prime converges. So all the assumptions of the lemma are satisfied, and therefore it follows from the lemma that the variance of yj wj, I'm always saying that y when I want to say w, the variance of wj are finite. This is by the lemma we proved. But the variance of wj, since yj is independent of yj prime, it's equal to the variance of yj plus the variance of yj prime. Since they have the same distribution, this is equal to twice the variance of yj, and therefore this shows that twice the variance of yj, it's finite. So, which means that the variance of yj is summable, and this is the third condition we want to prove. So up to now, we proved the first condition and the last condition. It remains to show that the expectation of yj is convergent. So this is the last step. Now at last, let me take zj equal to yj minus the expectation of yj. Right? So we know already that yj, the expectation of yj is well defined because yj is bounded by a. So this is a well-defined object, and well, the expectation of zj, it's clearly 0. The sequence zj, it's of course a sequence of independent random variables, because so are the yj. And finally, the variance of zj, Well, the variance of Zj, it's equal to the variance of Yj by definition of Zj. And we have seen that this series is summable. So the variance of Zj, it's summable. So now we can apply the two-series theorem. We have a sequence of independent random variables, or the one-series theorem, in which the variables have mean 0, and they have finite variance, and therefore by the one-series theorem, we get that the sum of Zj converge almost surely. But what is the sum? Well, the sum is Yj minus its expectation and this is, of course, the sum of Yj minus the sum of the expectation. And we know already, we proved already that the expectation, the sum of the Yj's converge. We have seen that in the second step. We argued that the Yj was converging because, well, they differ only finally many times of the Xj which are converging. So since this difference is converging and this sequence is converging, we get that this sequence is converging, and this is the second condition which we just proved. So in conclusion, so the theorem is proved, and recall the theorem was saying that if we have a sequence of independent random variables such that the partial sums converge almost surely, then whatever truncation we impose, the sums, these three series converge. And what's, as already said, quite surprising in this statement is that for a sequence of independent random variables, if these three series are converge for one A, then they converge for all A, which is somewhat surprising at first sight. But well, with the end of this proof, I conclude this lecture.